Well, good morning or good afternoon. I'm going to go over with you the mole review for 2016-17. I'm only going to go over questions, the part A of the questions. I'm not going to do both sets because they're both set up pretty much the same. Okay, so doing one should get us the other. So to begin with, you'll need to have a periodic table handy with you. So get your periodic table. I recommend the one in class. And you need a scientific calculator because you need to make sure you know how to use the one on the test that we're having. So for number one, so we're looking for what's the mass of 1 mole of titanium? Well, we just need to find the molar mass. So titanium, 47.8, we'll round that to 48. So the mass, this will be 48 grams per mole of titanium. So that was just straightforward. Molar mass, you just look it up. That'll tell you the gram atomic mass directly converts into the molar mass. Now let's see. Oh, I will do the half a mole of radon. So you need to look now. Radon is a noble gas, very large, and it's telling us in brackets here that 1 mole of radon would have a mass of 222 grams. So we're doing half a mole of this, so we could just say, okay, we got half a mole. So half of 222 is going to be 111 grams of radon, okay, because we're doing half a mole. And you could have taken the molar mass, 222, and multiplied it by 0.5 moles, and we would have got the same thing there. So let's see, what is the molar mass for the following? So for iron has a mass of 56 when you look it up. And there's 2 irons. Oh, okay, maybe I better write this a little bigger here for you. 56 times 2. And that's going to be 112 grams per mole for that one. And then we've got oxygen. Every oxygen is 16. We've got 3 of those. So that's going to be 16 times 3 is going to end up being 48. Okay, so we got there. So when you add those all up, it's going to end up being 160 grams per mole will be the molar mass for Fe2O3. When you're working on calcium, okay, I'm not going to go through, I'll just help you get it started here. You look on your periodic table, and calcium has a mass of 40. And there's just 1 of them. Now we've got oxygen next. Now oxygen is inside of the parentheses, so we've actually got 2 oxygens. Every oxygen weighs 16, and 16 times 2 is going to be 16 times 2. So we need to add those up there. That's going to be 32. And then let's see, we have 2 hydrogens here. Every hydrogen weighs 1, so we're going to have 2 times 1. So it'll be 40 plus 32 plus 2. You can do your own math there. Now for the rest of these here, I'm only doing the part A. So I'm going to zoom in now. Let me get this over here. Just focusing on this. So how many grams are in the following? Now I'm just going to draw a little MVP triangle. MVP, make a simple one so I can kind of have that to reference. We're looking for grams. How many grams? We're going to end up here, so we're going to have to be figuring some molar mass here. And we're given 0.25 moles. So we're starting right here with 0.25 moles. And then we're just going to, now since we're going away from the center of the triangle, we're going this way, we're going to multiply by the molar mass of silicon dioxide. So let's see, let's get this thing set up. I guess one of the things we should probably do is figure out what the molar mass of silicon dioxide is. Let's see, silicon is 28 when you look at it on the periodic table, 28 grams per mole. Plus we have 2 oxygens, and oxygen is 16, so 16 times 2 is going to be 32. So it looks like the molar mass for silicon dioxide will be 60 grams per mole. So we just kind of needed to know that because now 0.25 moles of SiO2, that's our given. That's right here. Now we just need to multiply it by the molar mass of SiO2, which is 60 grams. Now when we say multiply by the molar mass, we put the grams on the top. 60 grams SiO2 over 1 mole of SiO2. The moles cancel off. That's how you know you got it. And it looks like on that, well, at that point, you can do 60 times 0.25. I'm not going to get that one. That's going to be, 1/4 of that. Oh, okay, 15. And for part B, all I'm going to do is that it's set up the same, but now we've got sulfur dioxide, and you should come up that sulfur's mass is 32, and we still have 16 times 2, so it'll be set up the same as this one, but you're going to have a different molar mass because sulfur dioxide is a little different. Okay, number 4. Let's see, I'm just going to put my MVP triangle here to help me out. So moles, we're looking for moles. This is where we're going to end now. Let me scoot that over. So we're trying to find moles, and we're starting down here. In this problem, we got 24 grams of CH4. So this is our given, 24 grams CH4. So we'll get that over 1. That's our given. And since we are going towards the mole now, so we're going to divide. Anytime you're moving away from the outer part of the MVP triangle, you're dividing. So we're going to now divide by the molar mass of CH4. And let's see, carbon, when you look on the periodic table, it has a mass of 12. Every hydrogen has a mass of 1. Since we have 4 of them, it'll be 12 plus 4. And it looks like the molar mass for, this is methane, by the way. That's going to be 16 grams per mole. So now, what do we say here? We're going towards the mole over here, so we need to divide by the molar mass. And that should make sense, because we got grams up here in the numerator. So we want to put the 16 grams of CH4 in 1 mole of CH4. Since the grams cancel off, you know you have it set up right. And the answer will be 24 divided by 16. Okay, so there you go. I'll let you do your own math. It's going to be a little bit bigger than 1. I can just tell that. 24 is a little bit bigger than 1. Now for the second problem, carbon monoxide, every carbon has a mass of 12. Every oxygen has a mass of 16. You'll set up the problem just the same, except the molar mass will be a little bit different. So you just need to make sure you've got the right molar mass. The 12 plus 16 will be the molar mass of carbon monoxide. Now for number 5, I'm going to draw, again, MVP. A little roadmap for what we're doing. How many liters are in the following? So we need to end up over here at number of liters. That's going to be the volume. And we're starting, oh, that's nice, we're starting at moles. So it's just a one-step conversion. And since we are going away from the mole, we're starting at moles with 0.25 moles. And so we're going to, our magic number for multiplying between moles and volume is 22.4 liters per mole. So I'm just going to put the given here. So I'm just going to turn that into the given because I want to save spot. There's our given, 1/4 of a mole of oxygen gas. And all we need to do is, since we're going to the outside of the MVP triangle, we just need to multiply by 22.4 liters of O2 in 1 mole of O2. You don't have to worry about how heavy it is because we're not coming down here to mass, which would be grams. We just need to know that every mole of oxygen gas would be that. So now it's going to be 22.4 times 0.25, which that's going to be, let's see, well, half of this would be 11. Half of 11, the answer is probably going to be around like 5, I think, something, yeah, 5.6 or something. So there you go. So you can get that set up yourself. Same thing for part B. You know the moles. You just need to multiply by 22.4. You don't have to worry about, mass or anything on that one. So now number 6. How many moles? Getting the MVP triangle there, my little road map there, starting to look like the mall. How many moles are in the following? So this is what I'm going to end up with, and I'm starting up here at liters. So we're starting there. In this case, we got 33.6 liters. Well, it's just going to be the opposite of what we did up here. Here we started at moles, and we went there by multiplying by 22.4. Since we're starting up here with 33.6 liters, since we're going to the mole, you have to divide. Anytime you're calculating to the mole, to the middle, So I'm just going to be kind of lazy here and make that the given. Okay, we're right there. And now we're going to divide. And if you're not sure if you have to multiply or divide, look, you've got liters up here in the numerator. So your 22.4 liters of C3H8, liters of that cancels there. That's your check that you set it up right, and that is going to be 1 mole of C3H8. So it's going to be 33.6 divided by 22.4. And you know what? It looks like this is going to be about, oh, I don't know, it looks like it's going to be a little bit, oh, I guess the answer is like 1.5. So it comes out to be 1.5 moles of C3H8. And that, it just kind of was, you can guesstimate that. Number 7, how many molecules are in the following? So how many molecules? So I'm going to set up the mole triangle here, MVP triangle here. So how many molecules? The P down here stands for molecules, atoms, or particles. In this case, it's going to be molecules. So that's where we're going to end up. And we're starting right here. Oh, and how nice. 1 mole. So we got 1 mole of H2. Well, look, you don't even need to do a calculation. If you have 1 mole of hydrogen gas, how many molecules is there going to be? Well, 1 mole of anything is Avogadro's number. So the answer is going to be 6.02 times 10 to the 23 molecules of H2. Now, if you can't just look at that and do that, I get that. I had troubles with that too in high school. Here's the given, 1 mole of, oh, not H2O, of H2. Okay, that's the given. And then I'm going to say, all right, 1 mole of H2, okay, because that's mole of H2, is going to be how many molecules? Well, and we have to, since we're going from moles to molecules, we're going to multiply by Avogadro's number. So molecules of H2. So now we've got 1 times Avogadro's number. There's the answer. Number 8. How many moles are in the following? Well, MVP. I'm kind of starting to squish this one now, but okay, get it in there like that. Oh, that's terrible. I can't live with that one. Let me make that just a little bit bigger. There we go. Okay. So, how many moles are in the following? So, we're going to moles, and we're given molecules. That's down here at the particles. So, since I'm going to be quick, we're just going to make that the given. Okay, we have that many molecules of this compound, and we want to find moles. Since we're going towards mole, we're going away from the outside of the triangle, we're going to divide by Avogadro's number. So 6.02 times 10 to the 23 molecules C2H6 is 1 mole. And the molecules of C2H6 cancel here. So now we've got 1.5 divided by Avogadro's, 1.5 times 10 to the 23 divided by Avogadro's number. Well, I'm just going to go ahead because I'm just going to cancel off the times 10 to the 23. Now we've got 1.5 divided by 6, and I'm pretty sure 1.5, well, see, 1.5 goes into 3 twice. So I think the answer is going to be about, what do we get here? I think it's going to be about 4, isn't it? Oh, we'll actually do it 1.5. Now, if you didn't cross off the zeros, that'd be 1.5 times 10 to the 23 divided by 6.02. And that's going to be, oh, wait a minute. Yeah, it's going to be, it's going to be 0.25, not 4, because I'm dividing by Avogadro's number. Sorry, so 0.25, and that's going to be moles of C2H6. There we go. Okay. Number 9. Now this one's, since we're looking for atoms of hydrogen, we're going to first find molecules. Find molecules first. Then you're going to multiply by atoms. And I'll talk about that more. But so since we're looking for atoms of hydrogen in the following. So we are now given that we have this many moles of this. So the first thing we need to do, convert it to molecules. So I'll put that 0.75 over 1. And since we want to convert it to molecules, we're here at moles and we want to go to molecules. We're going to multiply by Avogadro's number, 6.02 times 10 to the 23. And that's going to be molecules in 1 mole of C3H6. So the moles cancel out there. And then, okay, I'm running out of room here. So then I'm just going to continue it on here. So now, what we want to do here, let me zoom out a bit. We've got molecules, so we're going to say 1 molecule of C3H6. We're looking for atoms of hydrogen. Every one of these molecules has 6 atoms of hydrogen. The molecules cancel out, not the times 10 to the 23, there we go. So now we're going to have 0.75 times Avogadro's number times 6. And I think, let's see, did I get that all calculated out? You ended up with something like 2.7 times 10 to the 24 atoms of hydrogen when you do that. So, number 10. How many grams are in the following? So I'm going to make a MVP triangle over here. Actually, I'll put it off to the side over here. Mole, we got the M, V, and P. So now this is the first of, now what's nice about looking at the MVP triangle, how many grams? We're going to end up here. This is what we're looking for, grams. But in this first problem, we're given liters. So we're starting up there. So we're going to have to convert to moles and then convert to mass. So we're going to start with 5.6 liters CH4 over 1. That's our given. And then since we're at liters, we need to change it to moles. So we're going to divide by the magic number of 22.4 liters of CH4 in 1 mole of CH4. Liters of CH4 cancels with liters of CH4, so we got that set up. So now we've moved to here. And now we just need to change this into grams by multiplying now by the molar mass. And carbon weighs 12. Every hydrogen is 4. So 12 plus 4 is 16 grams. So we'll say 1 mole of CH4 is 16 grams of CH4. Those cancel out. And now you're going to have 5.6 times 16. And then you're going to divide it by 22.4. For this problem over here, for part B, okay, so you are in this problem, it's going to be a 2-step problem. We still have MVP, but this time you're starting here. So you're starting here. This is where you're beginning. That's your given. You're going to turn it into moles by dividing by Avogadro's number, because that's how you convert there. And then you're going to multiply by the 22.4. So it's this number divided by Avogadro's number times 22.4. Number 11. How many liters, see, I'm going to kind of be lazy here and we'll kind of use this same one here. How many liters of gas, so we're looking for liters, are in molecules? Okay, well this is going to be kind of like similar to the problem there, except we're starting over here. So we're going to go from number of molecules, which is 44.2 EE24 molex of C5H10 over 1. So that's our given. I'm just shoving it all into one spot there. So we're right there. That's our given. We need to first convert it into moles because we're looking for liters of gas. So since we're going towards the mole, you need to divide it by Avogadro's number. 6.02 EE23 is 1 mole of C5H10, and I should put C5H10 there as well. And that's molecules. Molecules of C5H10 cancels there. And then the last step is, once we've got it in moles, okay, so these two will end up canceling each other out for the most part. Then we're going to volume. We're going to multiply by 22.4 liters of C5H10 in 1 mole of C5H10. Those cancel out. and we're going to have 44.2 times 10 to the 24 divided by Avogadro's number, and then we're going to multiply whatever that is by 22.4, or you can multiply these two numbers first and then divide by Avogadro's number. And number 11, I think it comes out to be something like 1,645 liters is how that one works. So this one over here is going to be the same thing, except you've just got, you're starting at molecules here. You just got, it's the same kind of problem, you just got a different given, so you just set it up the same. Number 12, how many molecules are in the following? So we're given liters of gas. So I'm going to come back and borrow this one. So for number 12, we're looking for molecules, and we're given up here. So we're going to have to divide by 22.4 and then multiply by Avogadro's number. Divide by 22.4, multiply by Avogadro's number. So I'm going to make this the given over 1. And to change this into moles, we say there's 22.4 liters of hydrogen gas in 1 mole of hydrogen gas. Liters of hydrogen cancel, so you know you set that up right. And since we're looking for molecules, now we're just going to multiply by Avogadro's number. 6.02 times 10 to the 23 molecules of H2 in 1 mole of H2. These are just a series of conversions. So now what you're going to end up doing is, well, looking at this, I can just eyeball this and say, hey, 11 divided by 22, that's a half. Okay, that's going to be 1 over 2. Half of Avogadro's number is going to be 3 times 10 to the 23. So there's your answer. Number 13, number of each atom. Don't make this harder than it is. Okay, now let's see. We've got 2 aluminums. Okay, so there's 2 aluminums. Now the chromiums. There's 2 chromiums inside this molecule, but we've got 3 of those. Actually, if that's to be a formula unit. So 3 times 2 is going to be 6 chromiums, okay? And then let's see now. If we just had 1 of these chromates in there, there's 7 oxygens, but now we've got 7 times 3. So there's going to be 21 oxygens. Okay, so there's that one. Don't make that one any harder than you needed to. Empirical formulas. Okay, I think the lowest common denominator here is divide each of these by 6, and that comes out to be CH2O. There we go, because those cancel off. This one we can divide each of those by 3, and so that becomes CH2. All right? And then for the last one, pretty obvious. Divide each of those by 2, and it just becomes HO. And that one was just the same as that. Oops, my mistake. Percent composition. So for number 15, first thing we need, okay, well, percent compositions are the part divided by the whole. That's all that fractions are. And so we need to figure out what the whole is, and by that we need to figure out the molar mass for tin chloride. And let's see, tin is 119 grams per mole when you look it up on the periodic table. Let's see, tin, 119 when we round it off. We've got 2 chlorines. Chlorines are 35, so that's going to be plus 70. And I think it works out to that we get the molar mass for tin chloride is 189 grams per mole. So that's going to be the whole. So we're going to be dividing by that for this problem. Now the part. So now let's do the part. Let's do tin first. SN. Okay, so in 1 mole of tin, we're going to have 119 grams of tin. And the whole weight is 189 grams per mole of SnCl2. So when we divide that out, we end up getting, let's see, you should get about 0.63, which would be 63%. And now you can do one of 2 things. You can say, since we only have 2 compounds in here, the amount of chlorine is going to have to be 63 minus 100%. I'm just going to set it up for chlorine. Let me scoot this over. Since now we have 2 chlorines in there, so we got to say there's 70 grams of chlorine altogether in 189 grams of SnCl2. And when you do the math on that, you end up getting, let's see, that's going to be about 37%. 0.37 is what you get on your calculator. Okay? Or you could have just taken 63, done 100 minus 63, and that would have worked out the same. So for part B, okay, 40 grams. Okay, we're just looking for percent composition, so don't worry about the 40 grams. We can just ignore that. 12 times 3 is going to be, oh, let's see what, that's going to be like 36 plus 8. So the molar mass for this compound is going to equal 44 grams per mole. So that's, oh, we got the part divided by the whole. So this compound we're going to be dividing by 44 grams per mole, excuse me. So let's figure out our carbon here first. Carbon, we said that there was going to be a total of 36 grams of carbon for every mole of this compound, and we said 1 mole of the compound is 44 grams per mole. So now you got 36 divided by 44, and that comes out to 0.82, which is going to be 82% carbon. And then let's see, now we could 100 minus 82 should be 18%. What was our other compound? Hydrogen. And if you're not sure, if you don't believe me, okay, well, the hydrogen, we said there was 8 hydrogens in there. So let's see, let's do now 8 divided by 44 equals, what did I do wrong there? 8 divided by 44. I don't know what I did there. Here we go. 0.18, and that becomes 18%. So this compound here, so again, we're looking for the percent composition, the part divided by the whole. So let's find out how much this whole thing weighs. Nitrogen is 14 when you look on the periodic table. We've got 4 hydrogens plus another one. Careful. So we got plus 5 for the hydrogens, because there's 5 hydrogens. Plus we have 1 oxygen plus 16. So I think when we work that out, we end up getting that equals 35 grams per mole for the ammonium hydroxide there. So the part, so let's see. Now we're going to do, I'll do nitrogen first. So I'll do nitrogen. The nitrogen weighed 14 grams over 35. Okay. And then for the next one, hydrogens. Now remember, there's 4 plus 1 more. 5 hydrogens, so 5 grams of hydrogen, because every hydrogen just weighs 1, divided by the whole, which is 35 grams per mole. Let me fix that, grams per mole. So that'll give us the percentage for hydrogen. And then oxygen, there's just 1 oxygen there. So let's see, we have 16 grams of oxygen over 35 grams per mole for the whole compound. So you can do the percentages there, and I think when we do that, we end up with, well, let's see, 14 divided by 35. Whoops, better use my calculator, right? 14 divided by 35 is going to be 0.4. And let's see, 5 divided by 35 equals 0.14. And then 16 divided by 35 equals 0.4. I'm going to round it to 0.46. So it becomes 4%, 14%, and 40%. 40% oxygen, 14% hydrogen. So now in this compound here, so we're going to D. How many grams of sodium are in 500 grams of this compound? So the first thing is we need to find the percentage sodium in this compound. Then we're going to multiply it by 500 grams. So we've got 23 for sodium, we've got 1 for hydrogen, we've got 12 for carbon, and then see 16 is the oxygen. 16 times 3, oh, I'm getting tired. 16 times 3 is 48. So we got 48 plus 12 plus 1 plus 23. The molar mass is 84 grams per mole. Okay, so the hint was find out the percent sodium. So I'm going to scoot this over now. So let's see, 23 grams of Na for every 84 grams of NaHCO3 comes out to be 0.27, if I remember. Oh, better double check. I don't want to. 23 divided by 84 equals 0.27, or 27% sodium. So now if we have 500 grams of this compound, we know 27% of that 500 grams is going to be sodium. So now it's 500 grams times 0.27. And let's see, 0.27 times 500 is equal to 135 grams of sodium in 500 grams of that compound. Number 16, what is molar mass and how do you find it? Okay, you go to your periodic tables and you add up all the weights of all the compounds, all the elements that are in your compound. So for H2O, for example, you would have to say every hydrogen weighs 1. So we got 1 times 2 plus oxygen. We only have 1 oxygen. Oxygen weighs 16. So 1 times 2 is 2 plus 16 equals 18. How many liters of water are in 12 decimeters? Well, we've got our conversion factors over here, so this should be pretty easy. So we've got 12 decimeters cubed. That's our given. And we are looking for how many liters of water? Well, it says here that 1 decimeter is the same as 1 liter. Oh, okay, well, it's going to be 12 liters. But if that doesn't work, you could say 1 cubic decimeter is the same as 1 liter. The decimeters cancel out, and you get 12 liters. Okay? Over here, we have 3,500 milliliters of water. We'll make that our given. And it says here we're trying to find, in this problem, we're looking for liters. Trying to find liters in there. Well, it says here that 1,000 milliliters equals a liter. So since milliliters is on the top here in the numerator, we want to put 1,000 milliliters in the denominator, would be 1 liter. And you're going to end up with, that's, oh, be careful. See, I might have thought that was 3.5. That's 3,500 divided by 1,000 will be 3.5 liters. Okay, so we're done, finally. Woohoo!